Buenos días. No, buenas tardes, casi.
Buenas tardes, profe.
Muy buenas, profe. ¿Qué tal?
Ya vengo, vamos a esperar a otros estudiantes. ¿Cómo están todos? Entonces, algunas preguntas antes de empezar. Temas generales y específicos.
Profesor. Profe.
Dígame.
Sí, yo tengo una pregunta sobre el deber, ¿le puedo hacer? En el deber, en la pregunta 6, nos pide graficar, por ejemplo, la derivada de E con respecto a K versus K. Entonces ahí, para ambas dispersiones, por ejemplo, para los electrones libres y para electrones en semiconductores.
Ajá,
Entonces yo lo que hice fue, para electrones libres tenemos la dispersión, la que tenía, la normal, la que era cuadrática, y la masa, y con la res más, la masa del electrón a
exacto.
3.
Ajá,
Y para, o sea, estaba leyendo, y para los semiconductores es básicamente la misma dispersión, claro que con un shift, o sea, contando la energía, el gap, pero en lugar de la masa del electrón tenemos la effective mass del electrón, porque ahorita ya tenemos en cuenta la interacción. Eso sería, para mí, la dispersión para los electrones en los semiconductores.
Fíjate que ahí les digo exactamente cuál es la dispersión, por eso el gráfico de abajo. Entonces, el
Ajá,
gráfico A es algo estrictamente cuadrático en toda la zona de Brillouin, desde menos pi entre A hasta pi entre A. Es
ya,
estrictamente cuadrático, de manera que la dispersión va a ser la misma en toda esa región de valores de K. Entonces, esta es muy sencilla, es del electrón libre, simplemente h cuadrado, k cuadrado entre 2m. Al tomar la derivada, la primera derivada y la segunda derivada, les va a dar un
una
solo
recta.
valor de velocidad que depende de k, y que es la primera derivada, y después
Ajá,
entonces la segunda derivada les va a dar un solo valor de masa, porque la
sí,
dispersión es igual en todas partes. Ahora fíjate la curva B. La curva B es solamente cuadrática en la vecindad de k igual a 0. ¿Entiendes? Ahí no toma, fíjate que no estoy haciendo énfasis en el gap, porque nada más presento la dispersión de la banda de valencia. ¿Ok? Solamente es la parte de abajo de la dispersión que siempre vemos, que es la banda de valencia y conducción. Esta es solamente la banda de valencia. Entonces te dice, mira, si eso es la dispersión, entonces ¿cómo se vería la velocidad y la masa como función de K? Entonces fíjate que cerquita de K igual a 0 vamos a tener cuadrático, porque todo mínimo es cuadrático, ¿verdad? Eso lo aprendimos en clase.
ya,
¿Ok? Pero en la medida que tú te vas moviendo hacia el borde de zona, que es donde está pi entre A, fíjate que la dispersión ya no es cuadrática. Empieza a ser más bien una dispersión cuadrática invertida. ¿De acuerdo? Fíjate que cerca de k igual a 0 tienes una parábola hacia arriba, mientras que cerca de menos pi entre A y pi entre A tienes como una parábola invertida. Entonces, es una parábola invertida cerca de pi entre A y de menos pi entre A. Entonces, fíjate que por lo menos la velocidad, ¿cómo va a ser la velocidad? La derivada va a ser positiva primero. Ok, imagínate en los valores, déjame compartir, perdón, esto debió hacerlo antes, que están discutiendo con una pantalla negra, me imagino. Aquí voy, aquí. Ah, no estoy conectado. Ah, está enchufado lo que no era aquí. Bien, entonces aquí donde tenemos la tarea. Aquí. Ok, ¿ven todos la tarea?
sí,
Perfecto. Entonces, como decía, en esta dispersión siempre cuadrática, ¿ok? Entonces, aquí va a ser una masa fija y una velocidad que depende de K, tomando la energía como simplemente h cuadrado K cuadrado entre 2m, que es esta dispersión de aquí. Aquí vemos que la dispersión es cuadrática en esta zona, de manera que aquí voy a tener, cerquita de K igual a 0, voy a tener una masa fija y una velocidad tal cual la tenía en la sección A, pero después van viendo que la velocidad primero va aumentando, ¿verdad? Con K, y después llega a un punto fijo y después va disminuyendo con K hasta que llega a 0 en el borde, ¿ven? Ok, aquí la derivada de la energía con respecto a K es 0. y por lo tanto la velocidad es 0 acá. ¿Ok? Cosa que no ocurre aquí. Aquí la velocidad sigue siendo una función de k, lineal de k. Aquí entonces ponen aquí y pueden hacer un dibujo cualitativo acá, ¿verdad? Simplemente empiezan con una velocidad que va creciendo y llega a un punto máximo que es aquí en el punto de inflexión de la curva y después va disminuyendo hasta que llega a 0. ¿Ok? Esa sería ese dibujo deben haberlo hecho en sólidos 1. Y después entonces la masa, ¿cómo se comporta la masa? Entonces la masa primero, la curvatura es hacia arriba, ¿verdad? Porque esta es la segunda derivada. Recuerden que la masa es 1 entre la masa, es la segunda derivada de la energía, es decir, la curvatura. Entonces primero tienen una curvatura hacia arriba, positiva, ¿ok? Entonces la masa es positiva. Después entonces llegan aquí a un valor límite de la masa. Y después entonces aquí empieza a ser la curvatura invertida. Entonces aquí la masa empieza a ser negativa. ¿Entienden? Entonces dibujen precisamente una curva cualitativamente, cómo serían las masas en la vecindad de k igual 0, y después cómo esta masa va cambiando. Fíjense que aquí yo tengo, justo en el punto de inflexión, tengo que solamente hay, la segunda derivada es 0. Entonces la masa aquí pasa de positiva a 0 a negativa. ¿Ven? Entonces hagan ese dibujo. ¿Se entiende un poco la idea?
Lo que pasa es que yo no entiendo, por ejemplo, para literal A,
Ajá.
me dice que como que hago un sketch, o sea, tengo que de ley hacer una gráfica, digamos, de cómo va la derivada de E con respecto a acá.
Correcto.
Entonces, o sea, por eso quería saber, o sea, yo podría hacer como que una especie de aproximación a cómo es la
Sí,
energía con respecto a acá, para el B, por ejemplo.
tomando en cuenta ciertos puntos emblemáticos. Vamos a hacerlo aquí, vamos a aprovechar. ¿Será que puedo hacer anotaciones acá? Eh,
O sea, para nada no hay problema, porque, digamos, ya se sabe exactamente cómo se comporta.
claro. Déjame pasar aquí a compartirles donde pueda dibujar. Aquí. ¿Ok? Para que tengan idea de lo que se requiere. Entonces, tenemos entonces la dispersión, las dos dispersiones que tenemos ahí. ¿Ok? Entonces, ya está claro la parte A y la parte B hace algo como esto. Vamos a hacerlo un poco más pronunciado aquí, o solamente de un lado, ¿ok? Lo que pasa por un lado va a ser igual por el otro. Entonces hace algo así. Y esta es energía versus K. ¿Ok? Entonces está claro que en esta zona, cerquita de aquí, entonces lo que hacemos es fijar varios puntos del comportamiento. Aquí va a ser cuadrático. ¿Ok? Entonces aquí en la vecindad de K igual a 0. ¿Ok? Entonces yo me pongo aquí y hago entonces un dibujo de la derivada con respecto a K de K. Entonces yo sé que aquí la velocidad primero va a ser 0, ¿ok? La derivada aquí de E respecto a K es 0, entonces esta sería la velocidad parte de 0 y teniendo en cuenta una forma cuadrática, ¿verdad? Entonces sería una constante por K cuadrado. Entonces tengo una derivada de esto, entonces me va a quedar de E de K va a ser alfa K. Entonces, eso va a ser una función lineal de K, y entonces saben que esta velocidad aquí al principio va a arrancar como una función lineal, ¿ok? Pero luego, entonces ven que aquí la velocidad llega a un máximo, ¿ok? Y después empieza a disminuir, de manera que la velocidad va a ser algo así como esto, ¿ok? Llega a un máximo y luego empieza a disminuir hasta que llega a 0. ¿De acuerdo? Entonces, simplemente hagan una correspondencia aquí. ¿Dónde llega el máximo? El máximo llega acá. ¿Ok? Este sería el K max. Aquí sería el K max. ¿Ok? Entonces, esta sería la velocidad. Primero aumenta, llega a un máximo que sería aquí en el punto de inflexión y después entonces va disminuyendo hasta que llega a cero otra vez. Y aquí está. Ese sería todo el gráfico. Y lo mismo para el otro lado, ¿no? Lo
¿Por
mismo
qué el
entonces...
gráfico sería
¿Ah?
como que, y por qué el gráfico sería como que liso? O sea, como que
Por-
es muy, ¿por qué no? Si tenemos, sí, o sea, si tenemos al principio una línea recta, por ejemplo, ¿por qué cuando
sí.
la velocidad empieza a disminuir, no disminuiría también de forma lineal? Ahí parece que estuviera disminuyendo como que, también como que un comportamiento cuadrático, la velocidad.
Sí,
Porque, o sea,
tiene una función que, claro, eso depende de los detalles de la curva que está planteada aquí. No te estoy dando la forma de la ecuación de la curva,
sí.
pero por ejemplo, esto podría ser un trozo de un seno, por ejemplo, de una función trigonométrica, pero como no te estoy dando esa forma, simplemente hacemos algo cualitativo. Sabemos que en la velocidad de cero va a ser cuadrática, entonces va a ser lineal. Entonces yo digo, yo sé que esta zona va a ser lineal, y luego entonces tengo alguna inflexión que no sé qué funcionalidad tiene, pero sé que llega a un máximo entre la zona donde la velocidad aumenta y después donde empieza a disminuir. Entonces, la velocidad aumenta hasta un cierto valor, que va a ser el Vmax, la velocidad máxima, y luego entonces empieza a disminuir hasta que llega a cero, y aquí está, disminuye y llega a cero. Eso es todo, digamos, lo que quiero apuntar en este ejercicio. Y después entonces, por ejemplo, en la curva negativa, fíjate que la pendiente siempre es negativa, pasa por un máximo negativo y después va a cero otra vez, ¿no? Que sería esta curva que iría por aquí, así, que hace así. ¿Ok? Entonces eso iría y sería algo así y algo así. ¿Ok? Entonces sería mi velocidad y entonces, bueno, ahora tienen que tomar una derivada de esa curva. ¿Ok? Entonces se ve que ahora derivan y entonces en esta zona lineal voy a tener una masa fija o una segunda derivada constante. ¿Ok? Y después entonces van a tener una masa que desaparece en este punto, porque tomo la derivada, entonces la segunda derivada, esta sería la segunda derivada de E de K, ¿ok? Entonces, la segunda derivada tendría un cero aquí, y después entonces sería negativa, ¿ok? Sería la pendiente de esta curva, ¿ok? Y así, entonces hacen el dibujo, y esto sí se los dejo a ustedes, tomen la derivada de esta curva, y obtenga entonces cuál es el inverso de la masa, porque recuerden que la masa efectiva que tiene es proporcional a la segunda derivada de E. De K. ¿Está claro?
Profesor, y por ejemplo, en el gráfico de la velocidad, al inicio tenemos un régimen lineal que corresponde, o sea, corresponde pues, al comportamiento cuadrático que hay cerca del cero. Ya, entonces, ese comportamiento cuadrático es similar al de los electrones libres, ¿verdad? Pero ahí la pendiente, o sea, la constante, por ejemplo, que acompañaría, digamos, en ese régimen, va a ser diferente, o sea, digamos, en los electrones libres tenemos la dispersión h al cuadrado sobre 2m por k al cuadrado,
Correcto.
que es, ya, esa sería la dispersión en toda la zona de Brillouin. Ahora, en los electrones para los semiconductores,
Sí.
podríamos tener un comportamiento similar alrededor del cero, pero en este caso cambiaría, en lugar de la masa, tendríamos la masa efectiva, justo en esa zona.
Exacto, porque entonces ahora toda la curvatura que tiene esto responde al potencial periódico, ¿verdad? De la red,
Sí.
y la respuesta de ese potencial periódico es lo que te da aquí. Entonces, en principio, esta relación que yo estoy poniendo para el semiconductor, ¿verdad? Que es algo cuadrático alrededor de K igual a cero, ¿verdad?
Sí.
Entonces, podrías modelarlo vía una masa efectiva, ¿verdad? Entonces, toda esa constante que yo estoy poniendo aquí, la modelo de esta manera por un factor cuadrático, ¿ok?
Entonces, si yo quisiera hacer como que una comparación, o sea, si yo tengo esa dispersión alrededor de cero y le hago la velocidad, pues me va a quedar una recta. Entonces, si yo quiero
Correcto.
comparar esa recta con la recta para los electrones libres, significaría
No, es
que
que
hubiera
son,
que tener
sí,
una pendiente diferente, o sea, una pendiente, por ejemplo, menor.
sí, sí, exacto. Por ejemplo, la curva de abajo, y digamos, no es lo que te pide el ejercicio, pero la curva de abajo podría tener una pendiente mayor pero lineal o menor pero lineal. Eso es todo lo que sabemos, porque no tenemos los valores específicos, ¿ok?
Claro.
Entonces, es un dibujo cualitativo para que ustedes sepan qué hace la velocidad como función de K para una dispersión tipo semiconductor, que es esta dispersión que está aquí. Así se comporta la banda de valencia, y la banda de conducción se comporta, como decías tú al principio, se comporta como algo así, ¿verdad? Y entonces aquí tenemos el gap. ¿Ok? Y entonces es lo que tú decías. Entonces ahora podríamos dibujar también la velocidad en la banda de conducción, que sería esta es la banda de valencia. Nosotros siempre dibujamos, como los semiconductores son aislantes, todos estos estados están llenos, ¿verdad? Entonces lo que hacemos es dibujar simplemente ahora este valor de la banda de conducción y este valor de la banda de valencia. Entonces este es el dibujo que siempre hacemos nosotros. ¿Ok? Y entonces, esta coordenada es energía, y esta coordenada podría ser espacio, por ejemplo, como lo vamos a usar ahorita. Puede ser espacio u otra cosa. ¿Ok? Algo que no donde no varíe la energía como función de esa variable. ¿De acuerdo? Do we agree? Yes? Okay, good. Okay, so let's open a new okay, so let's continue with what we were talking about yesterday. So yesterday we introduced the concept of mobility. Okay, so this is an alternative to conductivity. Okay, so mobility. Okay. So it's just another way of saying conductivity, okay? And we know there's a relationship between the two. Okay. So the mobility was defined in the following way. So we define a velocity, and we call this the drift. The drift, and let me put the full title so you know what I'm talking about. The drift with respect to the positive charges, okay? So this can be a vector, okay? And this should be proportional to the electric field, okay? And the proportionality constant is the mobility of the positive charges, okay? Notice that if this P means positive, okay, positive charges, so we're referring to the holes in the context of semiconductors, okay, so we know that if we apply an electric field, okay, we have positive charges, we apply an electric field, and the positive charges are going to move in the same direction. Okay, so this drift, okay, of the positive charges is going to go in the same direction as the electric field, okay? On the other hand, if we have the drift velocity of the drift of the negative charges, which are the electrons in this case in the conduction band, we will have again a proportionality to the electric field, and we will have a mobility, okay? But here we have to, we know that the electrons are going to move in the opposite direction, okay, to the electric field, so this has a minus sign. So we know that if we apply an electric field in this direction, and remember a student asked me about this in the first class, if we have an electron here, it will move in this direction in the electric field, okay? Because the force, okay, because of an electric field is Q times the electric field, okay? So it depends on the charge value. It can be minus for electrons and plus E for holes, okay? electrons and holes. Okay, is this clear? So this is very important, okay, because we're going to address different types of carrier transport, and this is one type of carrier transport, which is the drift, okay, drift carrier transport. This is what you would expect if you solved the equations of motion, okay, in of an electron in an external electric field, okay, carrier transport. Okay, so the other relationship we had now is that the charge current, for example, in the case of holes, the drift contribution, okay, we're going to have a diffusive contribution in the future. This then the number density, okay, remember to distinguish between the charge density and the number density. The number just counts the number of charges and doesn't account for the charge associated with that particle, okay? So this is the whole number density. And this is what we always talk about in the other expressions we derived. And then we multiply by the charge. So this is a positive charge times the number density times the drift, okay, drift velocity, okay, associated with the positive charges, okay? Okay, and if you substitute now the expression for the velocity, then this is E times P, and the drift velocity for positive, just substitute here the mobility, okay? This is the mobility. Okay, so it's a very easy relationship, very simple, times the electric field. Okay, the same we can do now for the electron, for the negative. I'm using this other, let me use here, we have an eraser here. Yes, good. Okay, so we have the negative drift current. Okay, so now again, we're going to have a velocity of the drift negative of charges. Okay, now we have the number density of electron. Okay, again, this is a number density, just counting the number of particles. Okay, times now the charge, and now the charge is the same as a whole, but with a negative sign. Okay, so this would be now the current, the drift current due to negative charges, and then we substitute again the relationship between velocity and electric field. So we get minus n, okay, minus n, then drift velocity. The drift velocity is minus the mobility of the negative charges, okay, and we have the electric field. Let me correct this. And to put electrons, but okay, so negative, the mobility of the negative charges. Okay, so you see here that we have a cancellation of signs. So we have E times N, mu N, E. Okay, so you see that both contributions to the current are positive, whether they have positive charges or negative charges. They're both positive, both in same direction. Okay, so this answers a question that a student asked me in the very first class. So remember this picture, this intuitive picture. So we have an electric field applied in this direction, and let's suppose we have positive charges and negative charges. These are electrons, these are holes. If we have the electric field in this direction, the positive charges move in this direction and the negative charges move in this direction. Nevertheless, taking into account both how electrons respond to the field and their charge, okay, they both produce a positive current in this direction here. So either N or P drift produce a current in the same direction. Okay, so putting those two together, we reach the total drift current due to both types of carriers. Remember that we can have together holes and electrons, especially for the intrinsic semiconductor. Any hole generated, any hole that is in the valence band is because there's an electron in the conduction band. So they're both going to contribute to the drift current. So now we have a common value for the charge. This is the absolute value of the charge, okay? And then we have the mobility of negative charges times the number density, and the mobility of the positive charges times their charge density times the electric field, okay? And that will be the total drift current. Okay? So that's one contribution. What's a relation? What is a relationship? What is the relation between mobility and conductivity? Okay, so remember our previous relations here. Here we have let me just write down the two relations again. So we have, for example, the mobility for positive, the drift current for positive charges for holes, and this was plus E, the mobility for positive charges, the number density for positive charges, and the electric field. And on the other hand, we had defined this relationship here, okay? This is the conductivity, and the conductivity was a positive density, E squared tau over N, effective mass, times the electric field. So you see that just comparing these two expressions, both are linearly, both refer to the drift current, okay? So just equating the prefactors of the electric field, we have the E squared tau over the effective mass, okay? So we get to cancel one charge, we get to cancel the density, so the mobility does not depend on the density, and we have the mobility of positive charges is E times tau over N effective N, okay? So you see that the mobility, the mobility is related to the response, right? So let us remind here, for positive is just mu positive times the electric field, okay? So you see that for positive charges, when this is how much speed or velocity in the vector, for the vector case, we expect from application of an external electric field. How easy it is to speed up a particle applying an external field. This gives you the mobility. So if the mobility is high, then a small electric field can generate a large velocity. If the mobility is low, then you need a large electric field in order to generate a large velocity. Okay, so this is kind of how susceptible the electrons are to be accelerated to a certain velocity. Okay, so comparing those two now, comparing conductivity and mobility, you see that the mobility is higher if we have a longer lifetime. That is, this is the time between collisions, okay? Time between collisions. Okay, so the longer the time between collisions, that is, the collisions are more and more separated. Okay, so they're more dilute. So we have a longer typical time between collisions. We have a higher mobility. The electric field is going to be it's going to be easier to accelerate these charges in the electric field. While, for example, if the mass of the particles is larger, then this gets small and the mobility is smaller for heavier particles, okay? So, for example, you could extract this effective mass from the dispersion, and if the curve is very steep, okay, so you have this will be light electrons, for example. Light electrons are very steep here, so high curvature generates a low mass, okay, and heavy electrons will be something like this, okay. This is energy versus K, okay. So this will be heavy electrons, and this will be light electrons, okay. So if you put that mass here, you expect to have a smaller mobility for the heavy electrons, and the larger mobility for the light electrons, okay. Okay, is this clear, the concept of mobility? And that's a connection between mobility and collision time and effective mass. Obviously, if the charge of the carrier is larger, then we have a better mobility. If the charge of the carrier is smaller, okay, we have a lower mobility. Okay. So we were discussing, any questions here?
No, Professor.
Yes? No questions? Okay. Okay.
No.
Okay, so remember that we're going to have we're going to mention different effective masses, okay? Depending on how you measure the mass, okay? We will define, okay, different effective masses. Okay, so we've already defined one, which was looking at dispersion. At the dispersion, we will call this the density of states mass. Okay, from dispersion. We know how to do that. The exercise we were discussing before is related to that type of mass. We also have the transport mass. Okay, where we determine, okay, transport mass from transport experiments. Okay, and there's going to be another one, cyclotron mass. Okay, from magnetic field measurements, Okay, so just so you're not puzzled by these different definitions, you'll see frequently in the literature, okay, the transport effective mass or the transport density of states effective mass, you know where they're taking these effective masses depend on the experiments you do, okay? So one thing that I wanted to illustrate, that I illustrated yesterday, was, for example, when you draw the dispersion relation in 3 dimensions, okay? This is something we know how to do. We can review some of the things you saw in solid state 1, but remember that close to k equals to 0, we have a way, okay, close. We have the dispersion which is spherical. Okay, we have a circle here. I'm going to train a little more this weekend to draw in geometrical shape. So we have a sphere here. Okay, so what would be the relationship between energy and these k values, well, you have h squared k squared over 2m x plus h squared k squared y over 2m. It's the same in all directions, right? Because it's a sphere. So this would be the equation of a sphere. Okay, so the masses are the same in all the directions, not only along kx, ky, kz, but along any direction. So isotropic mass. Okay. But what happens if I have a more real, or this is the I should put here the Fermi energy close to k equals to 0. Okay, what does this mean here is that if we look one dimension, E versus K, X, for example, this is going to be in the vicinity is going to be just a quadratic function. Okay, so this is describing in the X direction, is describing this expression here, and this is going to have a fixed mass around that vicinity. So I'm assuming, for example, that the Fermi energy is going to be somewhere here, for example. This is going to be the Fermi energy. Okay, so one thing that we have to do every time we're doing calculations is to know where the Fermi energy is and the dispersion in the vicinity, okay, dispersion in vicinity of Fermi energy. Okay, so we know that the Fermi energy is here, so the relevant dispersion is around that point. Okay, what's the dispersion of silicon look like? Silicon. So you did these drawings in solid state 1, for example, silicon in 3 dimensions, kx, ky, kz. You have these very strange lobes. So the Fermi energy is around these lobes here. And these are all the same distance to the origin. Okay. So this is where the electrons are. Okay, so we have to focus. So if we're accelerating something in the z direction, for example, we have to look. Okay, so we focus on this guy, and we draw our axes around that particular case, and we have something like this. Okay, kx, ky, kz. Okay, so we have all the electrons now inside this this volume here. Okay, and what would be now the description of this? We would have, okay, the energy now is the same, quadratic. Okay, but we now have a different mass in each direction because this is an ellipsoid. Okay, so this would be mx, and then we would have another mass in the ky direction in general, and another mass in the z direction. Okay, so this is the equation of an ellipsoid, right? And this will give me a different mass depending whether I accelerate it in the x direction or the y direction or the z direction. Okay, so that's the idea. Remember, you did these kinds of graphs when you were drawing the Fermi surface, and if you go from the first brilliant zone to the second brilliant zone, you get these kinds of pockets. And we can do that. I can put some of those exercises in the homework so that you remember what you did. This is at the beginning of solid state 1. Okay. Any questions about this? And then you can have stranger shapes. Okay, you could have, for example, ellipsoids where the cross section is circular. So 2 of these masses are going to be the same, and 1 is going to be different. Okay, and you can assess this. For example, this you would see in the cyclotron resonance. Cyclotron resonance. Okay? Okay, temperature dependence. Okay, so temperature dependence, we also mentioned two types. So we have, one is the lattice mobility. Okay, is limited by temperature. Okay, so the idea here is that this is going to be proportional to the inverse of the power of n. Okay, some theoretical developments say that this could be -3/2, but they vary from one super semiconductor to another. So this is not, okay, not universal. I mean, universal is that it is not valid for all semiconductors. Okay, so typically it's going to be an inverse power of the temperature. Okay, and this is the limitation of the mobility due to the fluctuations of the lattice. So if we have a lattice rattling around because of temperature effects, then these fluctuations of the lattice limit the mobility, okay, make for more scattering. So you see that this inverse temperature dependence says that at very high temperatures, you get this inverse power will make for a very small mobility because there's lots of fluctuations in the lattice. And for very low temperatures, then the mobility is going to increase. Okay, so the image of this is just, okay, I have my silicon atoms, okay, in the crystal, and temperature effects make these atoms oscillate, okay, just the fluctuations, okay, at a temperature this different from 0, and then the electron trying to move through the lattice gets scattered by these motions, okay, and it collides and it shortens the free mean path, the mean free path, okay, and it generates then a decrease, this function of the temperature for the mobility. Okay, the other source of scattering we saw was the ionized impurity source. Okay, so ionized impurity source, ionized impurity source, impurity scattering. Okay, so this is the fact that we have a silicon, for example, again the silicon lattice, and even at t equals 0, you have then, for example, a positive charge here, another positive charge here. So if the electron is trying to move through the lattice, it gets attracted by this ionized impurity. Another electron coming here, for example, could be scattered in this direction. So just because they interact with the Coulomb interaction, this is very strong interaction. So the dependence is a little different from the previous one. Instead of being inversely proportional to temperature, it's directly proportional to temperature. So this is going to be something like this. Okay, I expand this by mistake. Let me reduce it a little bit. Okay, so this is going to be proportional to the power 3/2. Again, this is not a universal power, but just I mean that it's a positive power of temperature, and then this is going to be inversely proportional to the number of donors that are ionized and the number of acceptors that are ionized, okay? So if we have more donors that are ionized and more acceptors, of course, this denominator increases and the mobility decreases. So this is the only thing that it says with respect to the concentrations. And then the interesting effect is that if you raise the temperature, then the mobility goes up. This means that raising temperature, raising T, diminishes the effect of ions scattering electrons, scattering carriers. Okay, so these are the two behaviors. These are going to be the big sources of limiting the mobility as a function of temperature. So we have thermal fluctuations on the one hand. So we have the oscillations of the lattice limiting the mobility of the electrons. Okay, and we have now the scattering with the ions in the lattice. Okay, that is going to also limit the mobility. Okay, so
Teacher.
yes.
Teacher.
Uh-huh.
Which effect would be the predominant?
Okay, so that depends. You see that it depends on how dilute the impurities are. So if the impurities are very dilute, then the lattice mobility is going to be the dominant. Okay, but it also depends on temperature. So it depends on this coefficient that's going to be here. There's going to be a coefficient. So depending on temperature, one may be dominant over the other, depending on dilution, okay? So in general, you have to take both of them into account, okay? One increases, for example, this is going to be very large, very, for large temperatures, this is going to be going to have a large mobility, okay? While for large temperatures, this is going to be a very small mobility. So you have to take both into account. Okay, they're both going to be present because we're going to be doping materials and we're going to do this at room temperature. So this is going to be important to discuss the two sources. But let's derive precisely how they combine. So this is a very interesting problem, okay? So imagine now that we have both impurities together. Okay, so you have the silicon, okay? And we have both fluctuations. Okay, so this is finite temperature, so each of them is fluctuating. And we also have impurities around. Let's suppose we have impurities like this. Okay, so an electron comes and it can scatter either of fluctuations or of ions. Okay, so it can first scatter here and it goes here and then it goes like this. Okay, because of the charge. So both scatterings present. Okay. So how do we combine both of these processes in order to, how to combine? Okay. So obviously, if there is a collision time associated with the lattice and the collision time associated with the ions, okay, how do we combine these two to get an effective collision time? Okay, so imagine that I have a situation where I have, let me not draw the ions, but I have let's put the fluctuations like this. Okay, let's imagine just a one-dimensional model. So we're going to have these fluctuations, and this is going to be associated with the time for lattice fluctuations. And then we have just one positive charge here and another positive charge here. So this will be associated with the time for impurity scattering, okay? So what do you think will happen? The electron is coming here. So, okay, he sees this, but then he's not going to see another positive charge, but for a long time. In comparison with the time he's going to see these fluctuations. So clearly here, the tau L is going to be predominant because he's going to, okay, I scattered from both the ions and the fluctuation here, but then I scattered all the fluctuation, I scattered all the fluctuations, I scattered all the fluctuations, and then I find another ion, okay? So what do you think should be the predominant effect in this case? Which of the two dominate? So naturally, it's going to be the one that has a shorter time because you encounter more fluctuations than impurities, okay? So the relationship is one that is familiar to you from circuits. The total or the effective collision time is going to be related with these other two in this way. Okay? So you see that the larger one, for example, the larger time, there's a larger time between collisions between impurities. This is going to be, the inverse is going to be smaller. So tau is going to approach tau L, okay? This is that relationship. So we have 1 over tau, and this is a very, very important relationship because it's really followed by materials experimentally. We have tau L plus 1 over tau I, okay? And so let's combine these. So let's sum the two fractions. So this is going to be tau L times tau I, and then tau L plus tau I. Okay, so we invert this relationship. We have that the effective tau is going to be the product of these two. Okay, so let's see one easy limit of this. Okay, so if tau L is much larger than tau I, we will consider the other situation. Let me backtrack here. So if tau L is much smaller than tau I, what happens with this formula? So we're comparing the two. Okay, so we have tau, and so this would be then approximated in the denominator by tau I. Okay, we have tau L, tau I. Okay, so you see that we actually derive this result I was discussing before. If tau L is much shorter than tau I, then tau L dominates, okay? Is the one that is going to produce the most frequent scattering. So it's the one that's going to dictate the temperature dependence, okay? So here you see that the shortest one, that is the shortest one according to this relationship, is the one that's going to give me the effective tau, okay? Notice another interesting fact that you may know about also. Let's suppose that we have tau L times tau I, tau L plus tau I, okay? Let's suppose again that tau L is the shortest, and notice what this factor is here. Is this factor greater than 1, smaller than 1, equal to 1? What is it? Who can answer? That factor is greater than 1, smaller than 1, equal to 1. What is it? Anyone?
repeat? I didn't understand the question.
So this factor here, tau I over tau I plus tau L, is this greater than 1, smaller than 1, or equal to 1? Come on, people. So we have tau I, and below we have tau I plus something. So this denominator is bigger than this numerator, right? So this is going to be smaller than 1, right? This here is going to be smaller than 1, always, okay? So something that is smaller than 1, okay, times tau L times smaller than 1, okay? So this means that the collision time, the total collision time or the effective collision time, is going to be smaller than the smallest. Then you saw this with resistor networks. Smaller than the smallest. Okay? This is of course due to the fact that if we have this, for example, we have a collision here, then we have a collision here. So actually the distance between impurities and fluctuations can be shorter than both of them, than tau L and tau I, okay? So you have another one over here, for example, then it could collide with this one, with this fluctuation, with this fluctuation, with this fluctuation, and then with the impurity, and that will be a shorter time typically than the other two, okay? So this is why we get this result, okay? So this is a very important intuition you should know about the behavior of this formula, okay? But in general, this is the way we combine. This is dominated by the smaller one and not by the larger one, okay? Because the larger one, the inverse is going to be small, so tau is going to be approximately equal to tau L. Okay, any questions about this? So let's recall what was the relationship between the collision time and the mobility. So these are all intuitions you should sort of incorporate, okay? So the mobility for the positive charges was let's put the scattering time, the scattering, let me not put any label on it, okay? So just the scattering over the mass. Remember this relationship, right? So the longer the time between collisions, the higher the mobility, okay? The effective mass of the holes, okay? So if I have this relationship here, okay, tau L and tau I, okay? We could just multiply by E, 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 so divide everything by E. We divide by MP, 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 both sides, okay? And what do we get? That the effective mobility now of positive carriers is due to the combination, okay, of impurity and lattice fluctuation. Wow, look how we combine. This is the way we combine mobilities. Okay, and if we have other sources of mobility, we just combine them the same way. So we have other sources of scattering, so other sources, we just combine them in the same way. And that's simply a logic of the collision time. 1 over the full mobility is going to be the sum over all the inverses of the different scattering mechanisms. Okay? Understood? Is it clear? Okay, so this is just the way we combine things in the mobilities and the collision times. We learned two things that are related, okay? Okay. Remember, we're going to use both types of quantities. So we're going to use both mobilities and conductivities because they're the most intuitive quantities. So remember that again, we have the drift current, the total drift current is going to be the combination, and this is the other way of writing it, the conductivity for negative and the conductivity for the positive charges, okay? In terms of the mobility, this is going to be the E times mu n plus mu p p e, okay? Remember the relationship between resistivity and conductivity. So this will be the total conductivity, sigma, okay? And the resistivity, okay, is going to be 1 over sigma, okay? So let me just make, as we're going to be addressing systems which different dimensionalities. We know that we learned in the common core that the voltage drop is equal to the I times R, okay? So this will be the current, okay, times the density, the charge density, times the length over the area, okay? So remember that this is the resistance, not the resistivity, the resistance. Sorry, this is not the charge density, this is the resistivity, okay? Sorry for repeating the notation, but this is also the notation used generally in the field, okay? So this is going to be the resistivity, and it's the inverse of the conductivity. But this is the way that we build the resistance. So the resistance is equal to the resistivity times these geometrical factors, okay? Geometry. So how long, okay? How long the material is, and what is its cross section. So this is the cross section of material. Okay, so again, if the cross section is large, the resistivity, the resistance is small. If the conductance at fixed cross section is long, then the resistivity, the resistance is large. Okay, if the resistivity is large, the resistance is large. So this is very intuitive. And the conductance, okay, is again the geometry dependent quantity. So this is going to be the resistivity, and now this is going to be this combination here. So as I increase the cross-section area, we get a larger conductance, but as I elongate the conductor, we get a smaller conductance. Okay, so this is the inverse relationship we have here. Okay, and of course we have the relationship between resistivity and conductivity. These are intensive quantities that depend on the material, depend on material. If it's silicon, germanium, or gallium arsenide, okay? While the resistance depends on the geometry. So for example, the resistance of silicon can be greater or smaller depending on geometrical effects, okay? Although the resistivity is the same. Okay, any questions about this? So this should be very familiar to you. Okay, so let's draw this as a function of dimensionality. So we have a general relationship for all dimensions. So let's assume that if you have a block of material, okay, what is going on here? So this would be the length, okay, And the cross section, this will be area, okay? So what's the area proportional to? If this is also L, and this is L, this is a block of characteristic size L, this will go like L squared, while the length goes as a length, right? Okay, so you multiply area times length, and this gives you L cubed, and this is the volume of the material, okay? Volume. In D dimensions, how does this work? So you see that this 2 is 1 less than 3 dimensions, so this is 3D, okay? Let's try to write this in D dimensions, in D dimensions, okay? So how does the area go? The area will go like 1 less dimension than the dimensionality of the system, which is 3. So this will go like L to the D minus 1, okay? 1 less here, so if D is equal to 3, 3 minus 1 is equal to 2. And the length goes as a length, okay? This is just 1 dimension. Okay, so let's write now the resistance as a function of L. So this will be the resistivity times L over A. And then we copy these relationships here. So this will be L to the D, L to the 1. Let me write it with it. So L to the D minus 1. Okay. And this will be L to the 2 minus D. Okay. So this will be now the relationship for any dimension. For example, in 3 dimensions, the resistivity would be the 1 over L. Okay, so it decreases with length. Okay, always referring to a block of a characteristic dimension L. Okay, in 2 dimensions, it will not depend on the geometry. Okay, and in 1 dimension, it will go as L. So it's 1 dimension is just a block of a line of material. So it just increases the resistivity as we increase the L. Okay. For the conductivity, I leave it to you to use the same relationship we had before, and this will be sigma times L to the D minus 2. Okay. Any questions about this? Okay, but the basic relationship is this one here. So whatever the transverse cross section is, whatever the length of the material is, this is the geometry, the geometric dependence of the resistance versus the resistivity. Okay? Any questions there? Okay, so let's combine a few things that we've done already. So we know that the conductivity is going to be, as we said before, related to the mobility, to this relationship here. The number density times the mobility plus the mobility of the positive charges times the number density of positive charges. Okay? Let's assume, okay, like it happens at room temperature, that all impurities, okay, all impurities are ionized. Okay, so this means that the number, the density of positive, of negative charges is given by the number of impurities that are ionized. If they're all ionized, then we can just put, okay, so this will be just N a donor. And then if all the acceptors are ionized, then this will be an acceptor. Okay? So this means that the resistivity, which is the inverse of the conductivity, is going to be 1 over that expression. Okay? Anyone not understand why I substituted P by Na? Remember that this, in the regime where all impurities are ionized, if the impurities are predominant over the intrinsic charges, okay, then all these positive charges, because these acceptors are ionized, so they make holes in the valence band, and the negative charges are all due to the donor impurities, which are going to be ionized, leaving positive charges in the ionic levels and negative charges or electrons in the conduction band. Okay, so we have this relationship here, and we see that then the resistivity is going to be an inverse function of the concentration. Okay, okay, so this is only in the limit where all impurities are ionized, okay, and the donor concentration is much larger than the impurity, the intrinsic carriers that we have in the system. Okay, in fact, if you do the experiments, okay, and you draw experiments, and you draw the resistivity as a function of impurity concentration, okay, concentration, you get a relationship like this. Okay, this will be a log. Okay, so it's logarithmic in both axes, so we get a straight line if we have an inverse power. Okay, so this is correct. Theory correct. Okay. Okay. If we don't have any impurities, let's see if someone tells me what should the expression for the mobility for the conductivity be. Okay. If no impurities, okay, what should I put here? We have this relationship. Yeah. What should I put in the number densities? Anyone? What should I put here? Only intrinsic carriers. What should I put there? I'm waiting for somebody who raise their hands. What do I put here?
We answered I.
Right, so we put the intrinsic electron concentration and the intrinsic hole concentration, which is the same because any electron that I have here is because I have a hole here. So Ni is equal to Pi, okay? And then we can write E times mu N plus mu E times I. So this will be the conductivity in the intrinsic case. Okay? So very good. Okay, I think you're following. Okay. Any questions? Anyone baffled at the fact that this might be Ni and these are both the same? Okay, remember that in the intrinsic case, okay, we only have electrons going from here to here, no impurity levels. So we make a hole here and we make an electron here. Okay? Okay. you must be asking another question related to the drift velocity. Okay, which is the fact that how is it that we can have something like this? So the velocity is equal to E times tau over m, that is the mobility, times the electric field, or the mobility. How is this possible? Okay, why do you think I'm asking this question? Imagine you apply an electric field and you have this relationship. Then the electron accelerates and accelerates and accelerates without any bound, okay? What happens, okay? What happens in experiments? Happens in experiments. This can't be true in experiments. The electrons just don't accelerate without any limits, okay? So what really happens in experiments? In experiments, you see something like this. The drift velocity as a function of the electric field. Okay, the drift velocities increase. Okay, for different materials, but they all saturate. Okay, and this is there's a limit here around 30 kilovolts per centimeter, okay? And this is about 10 to the 7 centimeters per second. Okay, so really the drift velocity does not increase any further. If I increase the electric field, we just achieve this, either this velocity or this velocity or this velocity and so on, okay? So they don't accelerate beyond a certain point. So carriers do not accelerate without limit. Okay, so this is a very important fact. The other fact, so this relationship cannot be forever, okay? Cannot be valid forever. Not valid forever. Okay, so it reaches a certain limit. So here the experimentalists come in and start to, you know, try to fit these curves with a certain relationship. So they propose things like this. For example, the velocity of the negative carriers are going to be some limit velocity, okay? And then something like this. So they fit their curves. This is nothing to do with theory, just fitting those curves. And they put a limit value for the electric field for negative charges. And then it turns out that these curves are well fitted by this relationship here, okay? In the small field limit, small e, okay, small e, this is very large, so we can neglect. Sorry, there's a factor here, square. Okay, in the small e case, and that's generally where you do the experiments. We consider only very small electric fields. Then this is going to be, so you see that small electric field, small with respect to this E0. Okay, this is much smaller than this value here, which you extract from experiments. So this is going to be very large if E is very small. So we can neglect 1 in front of this quantity, And we get that this is Bs times E over E0. Okay, so you see that this will be the linear relationship that we should measure. Okay, so this is only for E, and this is the precisely this behavior here is going to be linear with the electric field. And this coefficient here is the slope of this curve. Okay, slope. Okay, so we shouldn't apply this relationship for large electric fields. It's not valid for large electric field because you see that in this curve, it just flattens here. So this is only in the limit of E smaller than a certain limit electric fields. So this is important. We always consider, E smaller than a limit field, and this limit field depends, okay, depends on the theory. So we have no, unless we have a fundamental theory of this, okay, nonlinear effects in semiconductors, we have to rely on experiments, and we derive these relations from experiments and use them in theory, okay? So this is, you know, part of our fitting relations, or fitting or phenomenological or phenomenology. So, you know, when theories are lazy, or when theories, the theory is very complicated, you go measure things, you fit the relation to the data, and you derive things like this. And this is another way to approach the physical problem. And then you mix these relations in with some theory that you can do more fundamentally, and you obtain results. Okay. So let me finish with a comment that here that is really going to make it exciting to see this problem about the effective masses and the mobilities. Remember again the mobility, and this is why I'm going to mention this. The mobility is related to the charge, the collision time, and the transport effective mass. Okay, so imagine we have a band structure like we mentioned that we have for silicon. Okay, this will be again the energy against K, but let's remember that we had this graph that I showed you at the first lectures, that this could be the 1, 0, 0 direction, and this could be the 1, 1, 1 direction. These curves are always symmetric because they're semiconductor symmetric. So we draw the dispersion in one direction. Remember that we drew that. So we have something like this. So we have a certain curvature and then another curvature like this. Okay. And on the other side, we may have a totally different dispersion. So it may be more abrupt. Okay. And then it goes like this, and then it has another curvature like this. Okay, this was silicon. Okay, so imagine we apply an electric field here, and now I'm going to denote it by to differentiate to energy. So let me put here. This is going to be electric field in this direction, and we have energy here. Okay, so this is the dispersion. Okay, imagine now I apply and this is the conduction band. Okay, so take a look at what happens. So we have, let's suppose we have we're applying the electric field in this direction. So we have that we're going to start accelerating electrons. So the electrons are going to be here, here, and then they start to populate these, accelerate along the band, right? So this means that we have to follow the velocities generated by the derivative 1 over h of the energy with respect to k. So the electrons start to move in this direction, and they start to populate here. So like we in the exercise I put you, so initially they increase velocity, but then they decrease velocity even at a constant electric field. So the electrons start to move, they increase velocity, and then they decrease velocity, and then they stop Okay, even though I apply an electric field, they stop here, and then they go down the hill here. Now they start to move in the other direction. So they start to moving like holes. And then I reach a region again, which has another effective mass. So we have an effective mass 2 here, an effective mass 1 here. So you see the complex behavior we have when we have this band structure. First, we accelerate them like free particles with this mass, okay? They start accelerating, then they start decelerating, they stop, and then they start accelerating again in the opposite direction, and then they behave like free particles. So you have free particles here, free, and these are free, okay? But with they start with one mass, and they start with another, they end up with another mass. Another thing that can happen is that when I reach here, these two, the electrons can tunnel, okay? So they tunnel from one place to the other, and then suddenly we have a contribution from electrons that behave like free electron, but with another mass, okay? So here you see that the curvature is larger, so these masses are larger than these ones. These are light electrons, so M2 is larger than M1, and this actually happens for silicon, for gallium arsenide, for example. Gallium arsenide, when you accelerate in the electric field, you have one mass, okay, for the negative electron, because we are in the conduction band, is 0.067 electron masses. And in the other well, okay, so this would be here, and in the other well, we have an effective mass, which is 0.55. Okay, so you see the richness. So this is very, very rich behavior, okay, depending on the electrons, on the acceleration of the electrons. And this is actually telling me everything that's going to happen as a function of the electric field, which the experimentalists model through these kinds of fittings that they have with the measurements that they make. Okay, so let's stop here, and next class we're going to see diffusion. Okay, and this is going to be the final thing we would need to understand to start analyzing devices. Okay, so diffusion plus drift is all that the carriers are going to do as a function of, okay, concentration, gradients, okay, and external fields. Okay, any questions? Comments? Worries? Questions with respect to the homework? Okay, don't hesitate to write me if you have questions about the homework. We can either do a session like a tutorial, or we can do we can accumulate those questions for our next session, or I can answer you an email. Okay, so let's make the maximum contact possible. Okay, so don't hesitate to ask me questions about the homework. Okay, I will clarify just like I did with the first problem, with the other problem. Okay? Okay. So let me see who's still, okay, so we have quite a few students. So if you don't have any questions, so this is the end of the class, so you can run to your next, your next class. What class do you have after this one? Just so I know.
We have objetos astronómicos.
Okay, so Clara is waiting for you. Okay, so see you next Wednesday then. We may have a session, I will announce it, we may have a session next Tuesday to solve some other issues with the homework, okay?
Okay.
Okay, see you.
Bye, teacher.
Thanks.
Bye.
Bye.
Bye.